All right, 8.2 integration by parts. There's just a formula you use, and it's a pretty cool formula because it makes things really, I think it makes things a lot easier if you use it. And it says, hey, in this section, integration by parts, look at these. They're telling you, hey, look at these integrations. They look really difficult. We have an x, and then we have a natural log of x. If we called this u, du would just be 1. So we have this extra x in there. And there are no integration formulas, I don't think, on my 100. You can go look through your 100 integrations and you can see anything that matches those up. You might be able to find something. Probably not. So these might seem, oh, they're really difficult. But when you notice something like this, you see a natural log in there with another x, e to the x with another x, a trig function with an e to the x. If you see these, this is the formula we have to write down. So we have to write integration by parts, this formula down. So we start with this, and we end up with this. So you see, we're going to integrate, and then we have to do another integration. So what you have to do is clarify, okay, I have a u, but then whatever's left over, you say is dv. So you declare something as u, but then what's left over is dv. And if you have u, then you have to take the derivative of it to find du. If you have dv, you integrate it to find v. And then once you have all 4 of these, you just plug them into the formula. And then you'll still have to integrate this part. So it seems like it's hard. I'm going to say it takes a little longer than a standard integration, but the formula is right in front of you. You declare something u, you declare something dv, what's left over, and then you plug it in. Then you do u, then find the derivative of that. You dv, take the integration of that to find v, and then plug them in, and then do what we have to do. So, and they give you a few tips coming up. It says using integration by parts, note that you can first choose dv or you can first choose u. It doesn't matter which one you choose first. dv must contain dx. So when you do dv, it must contain dx. So if we look at this first one, I'm going to declare this one as u and this one as dv. So if u equals x, then the derivative of u equals 1. If dv, do you see how I put it on the bottom? dv is e to the x. When you integrate from the derivative of v to get to v, you have to integrate. When you integrate e to the x, what's the answer?
E to x.
Yeah, it doesn't change. That's why it's nice. That's a nice, easy integration. And they tell you, try to make dv the easier one because you have to integrate that. Taking derivative is usually easy, but sometimes people mess up when they integrate, when they go up. So this is it. This is all we have to do. So when we lay out our formula, it says u dv is our formula, and it changes to uv minus the integration of v du. That's the formula. We're just going to plug things in. u is x, v is e to the x. V ends up being e to the x, du ends up being 1. So I end up with x e to the x minus the integration 1 times e to the x is e to the x. And I already know what integrating e to the x is. It's e to the x. And I'm done. So, I mean, I like that formula when you have nice, easy integration and everything. And that's why we did this nice, easy one here, just to practice with this formula. But I mean, you have to have this formula ready to go. You have to understand. And then you have to label u and then v. I'm sorry, dv. I said du there, but it's dv. You have to label u and dv. There's u, and that's dv. There's u, and there's dv. And then take the derivative, find du, integrate to find v. All right. So I just wanted to show that. Let's see what else we have on here. There are several ways we could have did the same problem. They're just showing you, you could have made, and if you want to try it, I made x equal to u. I did it this way, but try the other way and see, you'll get the same thing. Oh, this was a little crazy. I don't know about doing it this way. Or even this way. I don't know about that either. I would think one of these two would be the easiest way to do it. And you should get the same way, even if you did it this way. So. You should get the same answer. Oh, this is just what I just did. And here are some clues, I guess, they want to show you. If you have x to a power with e to the x, x to a power with sine, x to a power cosine, they're saying make u x to the power. I mean, it's like a tip. And then dv, the e to the x. If you have x natural log, x arcsine, x arctangent, something with an arc or natural log, then u is going to be the ln or the tangent or the trig function. U will be the ln or the trig function, and dv will be the x to the power. So this is good to have next to you while you're doing some of these problems also. And then they have e with the sines and e to the power x with cosines. They're saying, hey, make the trig function the u and the e the dv. So these are some little tips, I guess, to make it easier. And that's out of the book, out of 8.2 section that came out of the book. So that's nice that they put that in there. If you have it sitting next to you while you're doing the homework and everything, it really helps to get familiar with this stuff. Okay, if we get a really hard problem like this, I mean, it looks hard at first, but there's another method of doing this if we don't want to use the formula. And I recommend trying this, the tabular method. I recommend trying this. Use the formula, like on the last problem. I wish that last problem we just did, we used the formula, but try using the tabular method on that. And I'm going to show you the tabular method here. And it's kind of cool. Here's an example. we make u the x squared. Oh, by the way, this is u. Let me go back and just see if what they hold is true. The sign is they're saying the sign is dv and x squared is u. So if we go back, I want to go back if it lets me. See, dv is the sign part in they're showing here. If you have the sign part, if you have x to a power, dv is the sign part. And then if you had e with the sign part would be u. But we just have a power. So we have the power, x to a power, and then we have the trig. So we're going to be using sine 4x as my dv. Oh, there we go. So if I write u, and this is called the tabular method, first of all. If I write u right here, that's u. I just start and then I put dv over here, which is v prime, same thing, is my sine 4x. And then all they say is just start taking the derivative. Just start taking the derivative. The derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. Once you get to 0, you stop. The derivative of sine 4x, right? This is u, and then du. If u is 4x, then du is 4. That's why we get the 1/4 out there, because we're missing a du. So we'll put a 4 here, we put a 1/4 on the outside. And then taking the derivative of sine to cosine, and then taking the derivative of this, you put another 4 down in the bottom. Taking derivative of this, you put another 4 on the bottom. So you take the derivative all the way down to the 0 part, to this line here of each one, till you get the 0 on the u, and then you stop here. You don't go anymore. Also, you have to alternate signs starting with a plus. Plus, minus, plus, minus. This is called the tabular method. And then your answer just pops up. This is the answer. You start off with u, and then you go to dv. So you end up with x squared and times a negative 1/4 cosine 4x. And then that's a plus. And then you go minus the next line, 2x, times a negative 1/16 sine 4x. And then you go plus 2 and 1/64 cosine 4x. And that's your answer. You just clean it up and put it together. And I think they do that on the next page. There we go. They clean it up and put it together on the next page. And there's really no integration. All you did was took the derivative of the u. It's kind of cool. You take the derivative, there's u, and then dv. You take the derivative of each going down. And we didn't integrate at all, but according to that tabular method, that's what you end up with, which is really, I think, a really cool process. So I would practice that. I had some students that just used that a lot, and it was It was kind of cool. And I never, I don't think I put it in that other video because I wanted to see some integration. But if you use the, if you're going to do instead of the formula, if you're going to use the tabular method, it's fine on a test or something to show your work. That's fine. I allow students to do that. I mean, they teach it in this section. I think it's a pretty cool method. And that is 8.2. So let's go to the homework. Now, if you go to the video for 8.2, you can see sometimes the tabular method goes a little longer. It's because, it's because when you integrate u dv, and you get the formula uv minus integrating v du, what happens sometimes that when you integrate this, it's not an easy integration, and you have to use the integration by parts formula again. In other words, then you're gonna, you're gonna say, okay, I'm declaring this as u and this as dv, and you're gonna go through that whole process again. You're gonna go for this one. So sometimes that might happen. And that's where the tabular method is definitely easier, where you don't have to do that integration by parts twice. Because you may see that, I'm not sure if you'll see that on the homework, but I've seen that before. Maybe it's on the homework, where if you don't use the tabular method, you have to do integration by parts twice in one formula, and the answer becomes longer. So that's where that becomes a little more tedious and a little longer and prone to making mistakes, where the tabular method definitely might be easier to do. Oh, I have the wrong thing I wanted to look at. So I'm just going to briefly go over a couple of things in 8.2. I don't think I'm going to do any of the problems, but just talk about a couple of them. Look at the answers and talk about them. Which ones did I want to do any? I don't really have any set up. We just look at it. And if you look here at this problem, we have an x to a power with a natural log. And I would verify this from that helper sheet that they gave us. Which one do we make u and which one do we make dv? So look at the one that says x to a power and then a natural log, and verify that they're making the natural log the u, so the other part is the dv. So if they have u equals natural log of x, then we have to find the derivative of u, and derivative of natural log of x is 1 over x. Then dv, well, I like to put dv down here, so it's the derivative is on the bottom. X to the 4, and when you integrate that, you get x to the 5 over 5. So now I have them all set up, u, du, v, dv, and you plug it into the formula, u, v, integrating v, du, and just plug them in. They plugged them in for us. This is what they got. X5 over 5 ln x minus the integration of v, which is x5 over 5 du. Du is 1 over x. So this is fine. We're actually done with this part. We just have to do this. And if you look, I have x5 and x1 here. So 1 cancels out. And I'm going to integrate this. So I add 1, I get x5, bring the 5 to the bottom. I have 5 down there already, so I have 25. 5 natural log of x minus this plus c. And if you look, I mean, if you type in this answer, or if you give me this answer for the show your work, we're done. They take it a little farther. They factor out, if you look at this, they factor out a 25. And when they factor out a 25 here, in order to factor out a 25 here, they have to put a 5 here, multiply that by 5, so they multiply this by 5, and they factor out an x5. So they factor out an x5 over 25. And when they do that, they're left with 5 natural log x. And when we take that out of there, we're just left with 1. When we take out x5, 25, we're just left with a 1. This is what I end up with. There we go. And that's the answer that they gave us. But once again, we're done right here. You don't have to simplify anything anymore. And I'm not a big fan that's what they do sometimes. Well, I think what they're doing is if they can factor anything out, they'll just do it for the hell of it. But if you type in this part into the homework or stop when to show your work, you get it correct. They understand that that is the correct answer. All righty, let's see what else we have here. And just more of the same. Once again, I will post this. It's just, and I'd have that sheet in front of me, because if you don't have this help, it wouldn't be wrong. You see, they're saying U is X, but it wouldn't be wrong if you label that U and then you label this DV. But that helper sheet tells you it's easier if you label it certain things, what they tell you. The problem should turn out to integrate and be a little easier if you do it their way. So I would have that in front of me for a while to make sure I'm doing it the way they want it at first. And then if you want to experiment and switch them around, make U the other, make U DV and the DV to U, you should get the same answer. And I've seen some people where they couldn't integrate it one way, but they can or take the derivative one way, but they can the other way. So it might be easier one way for you or the other way. Let's see what else we have here. Nothing exciting. So this one is a little harder. It's just busy. You need a full sheet of paper. You definitely need a full sheet of paper for this. Here's the problem. Just realize that this is x e to the 5x times 5x plus 1 to the negative 2. So here they're saying, oh, this is the dv and this is the u. And if you read through the book, they always say, try to make the easiest part dv. So they keep on stressing that. And this is really the easiest derivative. This might be it depends on how you look at it. It might be the easiest derivative, and they go through the process. If this is u, then taking, or did they do it the other way? The easiest integration, because you just add 1. And you see here's that you could change that to u du, would be 5. So then there's a 1/5 in here. And when you integrate that, you just add 1 and bring it to the bottom. So they do all that. That 5 goes down, this 1/5, 5 goes down to the bottom. That's why I said it gets really busy and you need a full sheet of paper. But try it, plug it into the formula. UV minus integrating V du. When you integrate U dV. So do the way they do it at first. They label this as U and this is dV. I would bring it to the top like this so it looks nice and pretty that way. And then you're going to just plug it into the formula. They plug it in. And then if you notice, this is a nice integration. They just use that as U. And then du is an extra 1/5, which down here changes to 25. So that one just gets a little busy. I mean, if you look, the formula is not bad, and the show your work part of these is not too bad. This is another tabular method, and some people just say blow off the tabular method. Don't blow it off. Definitely try it. I've noticed that some people who try it a few times, they start liking it a lot better. Look at this long, look at this answer that they create. So you start off by labeling something U, and then this is dV. So if we label this U, then the derivative of this, bring the 3 in front, you get 24x squared. Derivative of this, 48x. Derivative of that is 48. Derivative of that is 0. Then you stop. You alternate signs, plus, minus, plus, minus, plus. And we have sine x. And we start integrating, or start taking its derivative, sorry. Or start integrating. Did I say derivative? Yeah, start integrating. And you get negative cosine x, negative sine x, cosine x, sine x. And then you're just going, if I could be a little neater, this is the first part of the answer. This is the second part of the answer. Do you see with a minus in front? This is the third part of the answer. With the plus in front. Then this is the last part of the answer with the minus in front. So once again, the U's, I think I might have said it wrong when we looked at the PowerPoint. The U's, you take the derivatives, the DV's, you integrate. And you see, this is the answer. If you can combine anything, that works out great. And I think they do try to, well, the minus comes out in front. Here, minus changes to a plus. So they end up with this. And then me personally, I would stop here. Because we have the answer. But what they did was they looked at it looks like they looked at the signs and they factored out. There's the sign and they just took these things out in front. Same way with the cosines. They took negative 8x3 and plus 48x out in front. So there, I don't know why that extra step was needed, but because this is all what we're looking for here. So try that tabular method. This little box is really nice. Alternate signs. Find U and take its derivative as you're going down. Find a V prime or dV and integrate as you're going down. And there's another one you could take a look at. Same thing. You see they're integrating, you just add 1. 5 over 2, then you go 5 and flip up the 2. There we go. Add 1, so now you have 7 over 2. Put a 7 down here and 2 on the bottom, so you end up with 435. Add 1, you get 9 over 2, so multiply by 9, put a 2 up there, and this is what you get. The derivatives, and you always stop at 0. And then you just write out the answer. And try to simplify a little bit. I don't, they factored out, I mean, this 5 over 2, that's the 5 over 2. So when you factor out a 5 over 2, you're left with 2 over 2, which is just 1. And then once again, if you factor out a 5 over 2 here, you're left with 4 over 2, which is 2. So I'm assuming that's the 2, that's the 1, and then the other number was the 32. Okay, so I think that's it. That's 5.2. Like I said, try, I mean, on number 10, just try the tabular method and see, I mean, use the formula, try the tabular method, try them both. And I think you may like the tabular method better. All right, stop recording.